Hello everyone, I am Dr. Osman reporting from the University of KwaZulu-Natal, South Africa, the premier University of African Scholarship. In our previous lectures on material balancing, we've looked at how we write up a material balance on single unit processes containing perhaps just a single separator. And by now you should be well versed on the notation as well as how to write up a material balance and how to solve a material balance, whether it be sequentially or simultaneously. You should be able to know how to write up a total material balance as well as component balances in terms of mole fractions and molar flows, or in terms of mass fractions and mass flows. Okay, so far you have learnt also the basics on drawing up a degree of freedom table, how to count the number of independent variables, the independent balance equations, the number of independent flow and composition specifications, and also the number of subsidiary relations, independent subsidiary relations. And you should be able to know from that information on how to calculate your degree of freedom. In this lecture, we extend our knowledge to multiple unit processes containing perhaps different or two or more separators as well as mixers and splitters. And so far you have already, although you have known how to construct a degree of freedom table, you may not have grasped the usefulness of this degree of freedom table up to this point for single unit systems. However, you shall now see the value of a degree of freedom table in providing some direction on where to start with your material balancing and also where to continue with your material balancing when it comes to multiple unit systems. It can be very complicated, and this is where your degree of freedom table will help you a lot. So let's begin. Okay, now let's look back at our previous example containing a single separator, and you're probably really sick and tired of seeing this example. However, it's just a good illustration. Now note that with a single separator, things were quite simple, right? We just have one separator. The entire process consists of only the separator. If I had to draw an overall balance, a box over this process, it won't make any difference at all, as you can see. And also there are no inner streams to worry about. Everything crosses the box, so the overall process, so whether we are looking at a unit process or whether a standard process, it's a single unit, so it's the same thing over and over again. However, things get more complicated when there are more than one separator or more than one unit, in fact. So now let's finally depart from this example and go on to something more complicated. Okay, and this is a two-stage distillation process, and it's designed to separate a three-component mixture, benzene, toluene and xylene, into three streams. Each of them, of course, will be rich in each of these three species. Okay, so we are given a feed. This is stream 1, and we are told what the feed rate is, so we can immediately say that N1 is 1000 moles per hour, and we are given the composition as well. So we are given X1B, for example, to be 0.2, and X1T is 0.3, and of course the rest will be xylene. That's a dependent variable at this point. We are not told anything about the flows of the overhead and the bottoms of this first column. However, we are told that the bottom's composition consists of Okay, so X3B would be 0.025 to 2.5%, and X3T for toluene is 0.35, and that's out of column 1. We are not given the composition of the overhead or the flow, so we have absolutely no information on the flow. Okay, I'm going to have to try and juggle between different zooms here, so just bear with me. Okay, we are thereafter told that column 2 has 8% benzene and 72% toluene. Oh yes, one piece of information that we are told about the overhead is that there is no xylene in the overhead. Okay, so that's just benzene and toluene. So let's look at the overhead product for column 2. So X4B is 0.08 and X4T is 0.72, and the rest will be xylene, of course. And now we need to determine how much of material will be processed by each unit and how this material will divide among the outlet streams. Okay, so take note of what they want us to solve here. Essentially, they want to know how much of moles will be coming out of the overheads and the bottoms of the columns. Okay, so now if we take a look at this process, it has two separators, right? Two columns. It makes things more complicated because we have one unit here which we can write a balance over, right? The column 1 with 3 streams, and then we have column 2 also with 3 streams. However, stream 3 is common to both columns. So if we solve a balance around column 1 and we obtain some information on stream 3, then we can use that information in column 2, or vice versa. But at this point we don't really know where to start. We have some information for column 1, we have some information for column 2. How do we know which one is well specified or completely specified or solvable? How do we know that any of this is solvable? Perhaps there's just not enough information at all, despite how it looks. It looks like it may be a lot of information, but perhaps it's not. Also, another issue is that if we look at an overall balance, okay, drawing a box around the entire process, then we see that only 4 streams actually cross the box. So stream 3 is an inner stream, an internal stream, so that will have nothing to do with the overall balance. So contrary to our previous example, which had just one column and ultimately just one balance, an example like this, which contains just 2 units, complicates the issue significantly. So let's look at our degree of freedom analysis for this process. Okay, so as previously discussed, we could write potentially 4 types of balances. We could write a balance around unit 1, column 1, a balance around column 2, or we can consider the process and write down every single balance that we can possibly obtain and solve everything all together, which is a very tedious option. Or we can start by solving the overall balance. Now, either of these balances could be a good place to start. Or perhaps there's only one of these units that would be a good place to start. Okay, so firstly, let's just fill in this degree of freedom table, and we conduct this in a similar fashion as our previous example. So let's look at it in some detail. Let's consider Unit 1, the number of stream variables. Okay, as before, we simply count the number of components in each stream. There are 3 in the feed, 3 in the bottoms, and 2 in the overhead. So that's 3 plus 3, 6, 7, 8. So that's how we get our 8. Number of independent balances, we simply count the maximum number of components associated with column 1. Okay, and there are a maximum of 3 components associated with the column, even despite the fact that the overhead only has 2 components. Okay, so we count the maximum number of components, and that will give you the number of independent balances. Okay, so let's look at the number of specified compositions. We have 2 compositions in this stream and 2 in this stream here. Now, by default, we can easily calculate the composition of toluene in either of these streams. However, that won't be an independent specification. So we are only counting independent specifications. So we have 1, 2, 3, 4 compositions. We are only given one flow, and that is the feed flow rate. And at this point, we are not given any subsidiary relations for this particular unit. In fact, for this particular example, there's no subsidiary relations. Okay, and solving the degree of freedom, we can see that 8 minus 3 minus 4 minus 1, we get a degree of freedom of 0. Let's solve the degree of freedom for unit 2. Okay, counting very similarly, we have 3 here, plus 3 components, plus another 2, so that will give you 8 independent variables. Once again, there are a maximum of 3 components associated with column 2, so that's 3 independent balances. There are 4, right? 1, 2, 3, 4 specified compositions. However, there is no specified flow associated with column 2. Okay, so that's a 0 there, and there's no subsidiary relations. So 8 minus 3 minus 4, that will give you a degree of freedom of 1. Now let's consider the process. When considering the process degree of freedom, we have to count everything in each stream. Okay, so we can look at, let's count the number of stream variables. We have 3 here, plus 3, that's 6, 7, 8, 9, 10, 11, 12, 13. Okay, so in our process we have 13 stream variables in total. When it comes to the number of independent balances, note that we had 3 independent balances for column 1 and 3 for column 2. Now in the case of our process, we can simply add the number of independent balances. Okay, so that's 3 plus 3, and that will give you 6. Okay, considering the number of specified compositions, we have to count it again. Okay, we have 1, 2, 3, 4, 5, 6. And once again, just one specified flow. No subsidiary relations. So our degree of freedom for the process will be 13. 13 minus 6 minus 6 minus 1. so that's 0. Now let's look at a balance over the overall, right? If we draw an entire box over this, then we can look at which streams cross that box. We can do a balance as such. So let's look at the number of stream variables, independent variables. We can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, remember that we are neglecting stream 3 because for the overall balance, stream 3 is of course an internal stream. It doesn't cross the overall box. In terms of the number of independent balances, we use the same approach as any particular unit. So there are a maximum of 3 components associated with the whole balance. So that's 3 independent balances. In terms of our specified compositions, we would have 1, 2, 3, 4 compositions, and once again 1 flow. And no subsidiary relations, so we have a degree of freedom of 10 minus 3 minus 4 minus 1, so that's a degree of freedom of 2. Okay, now let's look at this degree of freedom table. Okay, the first thing to note is that we have a degree of freedom of 0 for our process. Now, if the process degree of freedom is 0, then it is a sure sign, a 100% positive sign, that the entire system, right, the entire process is solvable. Okay, so this degree of freedom for the process being 0 is the defining factor, the defining trait that the entire system will be solvable. However, let's look at the other balances, the other degree of freedoms. We note that for unit 2, the degree of freedom was 1. Okay, it's greater than 0. It means that if we attempt to solve the balance for unit 2, we will still be stuck with one variable that is unsolvable. The overall degree of freedom is even worse. A degree of freedom of 2, and this indicates that we would, if we attempt to solve the overall balance, we will be stuck with at least two variables that are not solvable. However, if we look at unit 1, unit 1 has a degree of freedom of 0, and this means that if we attempt to write out all of the balances for unit 1, we will be able to solve each and every independent variable associated with unit 1. So what this degree of freedom table is suggesting is firstly that the process is solvable, and the best place to start would be drawing up a balance for unit 1. Okay, it won't be a good idea to start with unit 2 or the overall at this point, simply because we have a degree of freedom that's greater than 0, and ultimately it means we won't be able to solve these units if we start with them. But can we solve these units once we finished solving for unit 1? Okay, and that's something worth checking out. So let's continue with the balance for unit 1. Just a quick note before we begin writing out our balances for unit 1. Note that the process degree of freedom is 0, which means that we could also solve the entire process However, this is generally very tedious, so we avoid this. The way to go about doing it would be to write out 6 balance equations and solve for 6 equations. Solving for 6 equations simultaneously can be quite a nightmare, especially if you're not using any computer software. So therefore, we will proceed with the balance on Unit 1. Okay, so let's look at our material balances for Unit 1. If we draw up a benzene balance, we can see that we have 0.2 times 1000 or 200 moles per hour of benzene coming in, and we have benzene coming out in the overhead as well as the bottoms. So we write out the balance accordingly. Okay, so what comes in, the feed, must equal to what comes out, which is the two products. So we have the mole fraction, X2B, times your moles for your overhead, plus the mole fraction, X3B, which is equal to 0.025, times the molar flow rate, N3, which we currently do not know. We can write out similar balances for toluene, 300 of toluene coming in, and the following coming out. Okay, we are expressing our toluene mole fraction in terms of our benzene mole fraction, because that is the dependent variable in this case. And for our bottoms, we know that X3 toluene is 0.35, so that's 0.35 times N3. And then we can move on to xylene as well. Okay, note that if X1B is 0.2 and X1T is 0.3, then by difference, X1X should be 0.5. Okay, 1 minus 0.2 minus 0.3. So that's 0.5 times 1000 moles per hour. So we have 500 moles per hour of xylene coming in. And we also noted that there is no xylene in the overhead, so all of the xylene coming in here should equal to what's coming out here. Okay, and we can express this in terms of our mole fraction and our total flow, which we currently do not know. So that's 1 minus 0.025 minus 0.35. Now we could have also written up our total balance. However, there are only 3 independent balances. We've written 3 independent balances, and the 4th one will of course be dependent. So it won't add any value to our calculation towards solving for our unknowns. We can immediately note that we can solve for N3 using the xylene balance. It's the only unknown. So we can solve for N3 in this way. Thereafter, we can solve for N2 and X2B simultaneously. Okay, so we obtain N3 to be 800 moles per hour. And we can do some manipulation between our equations to simultaneously solve for our total flow for stream 2 and our mole fraction of benzene in stream 2. Okay, and we obtain the following results. So let's look at what we have actually solved here. Okay, we have obtained N3 to be 800 moles per hour. Okay, so we can write it down here. N3 is now 800. We've also solved for N2 to be 200. And we know that we've solved that X2B is 0.9. And X2T is very easily solvable. It's just 1 minus 0.9. So we can obtain X2T to be 0.1. So where do we go from here? There are two possible options now. We finished solving the unit 1 balance. Now we can either proceed with trying to solve the unit 2 balance, column 2, or we can solve for the overall balance. Perhaps that might give us a better route or a more easier solution. Let's have a look at which idea is better. So now we go back to our degree of freedom table. And let's look at what has changed. In the case of unit 2, we now have one specified flow. Okay, N3 was previously unknown, but now it is known. So now we have one flow. Okay, and I'm just writing that in red. Nothing else has changed for stream 3. Everything is solved. So now we can calculate our degree of freedom for unit 2, and it becomes 0. So now it tells us that if we attempt to write out our balances for unit 2, we will be able to solve for all of the unknowns associated with unit 2. However, let's look at the overall balance. Has anything changed? One thing has changed. We have specified, well, what was previously not known is our flow rate, N2, as well as our composition. So both of that is known now. So instead of having just 4 specified compositions, we now have 5 independent specified compositions. And we have one more specified flow. Note that the information for stream 3, although it was solved, is irrelevant to the overall balance. So we do not include that for our overall calculations here. So now our new degree of freedom, this will become 2 now, will be 10 minus 3 minus 2 minus 5. So our new degree of freedom for the overall is 0. So in this particular example, what we are being told is that from now on we could proceed with solving either unit 2 or the overall balance, and we will be able to solve for all of our unknowns. Now, what has changed for the process? Do we care about what has changed for the process? And the answer is no. We have predetermined that we have a degree of freedom of 0 for the process initially. So it means that the entire process is solvable, definitely solvable. Now that we have solved for certain variables and certain variables have become specified, the degree of freedom for the process may end up to be negative. Okay? But that does not concern us. The process degree of freedom can be negative. That does not matter. So we could choose either to proceed with the balances for Unit 2 or the overall. If we proceed with the Unit 2 balances, we obtain the following. Okay, so if we look at benzene, we have benzene coming in at stream 3 and all of it is going out through stream 4. Okay, there's nothing in the bottoms. So we can write a relationship between stream 3 and stream 4. Remember that we already know what N3 is. And we can write similar balances for toluene and xylene, which are in all 3 streams. So we know what the input is. We simply express the output. Okay, so 0.35 N3 is equal to 0.72 N4 plus X5 of the toluene times N5. And we can express the compositions for xylene in terms of the compositions for benzene and toluene. And we can write out the following balance. From this balance, it's very easy to obtain N4 using the benzene balance. Thereafter, we need to solve for X5T as well as N5, and we can do that simultaneously. Okay, we can add our balance for toluene and our balance for xylene together, combine our equations and solve. Okay, that is just simple applied mathematics, first year level, even high school level. Okay, and finally we obtain our N5 and X5T. Okay, let's go through some notes here. Okay, as I've mentioned, we started to solve the example from equations describing unit 1 because this was the unit that had a degree of freedom of 0 and everything else had a degree of freedom that was greater than 0. Okay, so our degree of freedom table is actually very useful in giving us a good direction on where to start and also where to continue. And you will continue to see the value of a degree of freedom table as we go through more and more complicated examples with more than 2 units. Okay, could be 3, 4, even 5 units. And we will have to solve the degree of freedom for each unit as well as the overall and the process. Okay, another recap. The number of balances for the process is the sum of the balances for the individual units. Okay, remember that for the process, I simply said here 3 plus 3 is equal to 6. Okay, so that's simply adding the balances for each individual unit. You do not add the overall balance. Okay, so for the process, you simply add 3 plus 3 and that's equal to 6. And that is the only time when you add figures for units to obtain the process units, the process balances. You do not add the number of stream variables for unit 1 and 2 to obtain the process. You do not add specified compositions or subsidiary relations or anything of that sort. The only time when you have an addition, an easy addition, is when adding the number of independent balances for each unit to obtain the process balance. I've seen many students make this mistake, where if they don't really know what's going on, they simply try and add everything to obtain the process, and that's incorrect. It's incorrect because we may have some duplication of variables between our units. Okay, if we look at our independent variables for these two units, if we're considering unit 1 and unit 2, these independent variables here in stream 3 are common to 1 and 2. So if we simply added these up, then we would have some duplication, we will have an incorrect result. Whereas if we simply count the independent variables for the process, we will only count this internal stream once, or this common stream once. Okay, so to conclude, the solution will always start from the unit for which the degree of freedom is 0. Now let's look at a slightly more complicated example, and we're just going to look at the degree of freedom table, how to draw up a degree of freedom table for this particular example. Okay, this is a 4-stage evaporation system, and we have a 50 weight percent sugar solution. So we are given the mass flow rate of the sugar solution, and it is going into a 4-stage evaporation, okay, in order to make the sugar solution more concentrated. So with each evaporator, we have a removal of water and a concentration of our sugar. Okay, so it's a 4-stage evaporation system. 50% by weight sugar solution is concentrated to 65% by evaporating an equal amount of water in each of the 4 stages. And with a total input of 50,000, a product stream of 35,000 is produced. And they would like to know if you can determine the compositions of the intermediate streams, in other words, the compositions of stream 3, 5, and 7. So let's look at the degree of freedom analysis for this particular example. Okay, another point that I would like to make before we go on to the degree of freedom analysis is that we need to read the question very carefully in order to extract the relevant information. Okay, remember that it said that a 50% sugar solution is concentrated to 65% by evaporating an equal amount of water in each of the 4 stages. Okay, and that is ultimately a subsidiary relation that they are telling you. Okay, they are telling you that F2 is equal to F4. They are saying that F4 is equal to F6 and F6 is equal to F8. So very subtly they have given us 3 subsidiary relations. So the lesson is that we need to read our question very carefully to extract as much information as possible. So let's look at the degree of freedom table. Okay, I've drawn up a table here consisting of unit 1, 2, 3 and 4, as well as the process and the overall. So let's proceed. Counting the number of stream variables, we have a 50% sugar solution here, which obviously implies it's 50% of water as well. So we have sugar and water, so that's two components over here. We still have a sugar solution here, so we still have our sugar and water. But here we only have water. So the number of stream variables would be 1, 2, 3, 4, and 5. So that's 5. There are a maximum of 2 components associated with unit 1. So our maximum balance, our balances is 2. Let's look at our number of specified compositions. We only have 1 composition specified, and we have 1 flow specified. Now, regarding our subsidiary relation, we note that they are giving us a relation between F2 and F4. Now we don't have any information on F4 or F6 or F8, so ultimately we can determine that the subsidiary relation will be irrelevant when solving the balance for this unit, because it's not relating anything between our streams in question. So our number of subsidiary relations here will be 0. So for our degree of freedom, we have 5 minus 2 minus 1 minus 1, a degree of freedom of 1. Now let's move on to unit 2. Okay, a very similar situation. We have 1, 2, 3, 4, 5 stream variables, 2 balances. However, in this case we have absolutely no specified compositions and also no flows. So our degree of freedom is simply 5 minus 2, and that's 3. Okay, that's quite a high degree of freedom. Also, once again, our subsidiary relation cannot help us, so it's not worth counting. It's not relating to any of our streams 3, 4 and 5, which is relevant to unit 2. Okay, let's look at our third unit. And for our third unit, we have once again sugar, water as well as water, so that's 5. 2 balances once again, and no specifications or subsidiary relations. So once again a degree of freedom of 3. Now on to our final unit. Once again 5 stream variables. Okay, that's sugar and water there, sugar and water here, and only water in stream 8. So that's 5. 2 balances. We have 1 specified composition and 1 specified flow. Our subsidiary relation once again does not help us. So we have again a degree of freedom of, that is 1. 5 minus 2 minus 1 minus 1. So that's a degree of freedom of 1. Now counting the process stream variables, we go about this quite thoroughly. Okay, number of stream variables 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that's 14 stream variables. Remember, we can just add up these balances here to obtain our process balance. In terms of our specified compositions and flows, we have in the entire process 2 flows and 2 compositions. And when counting the subsidiary relations for our process, our subsidiary relations must always be included in our process. Okay, so we have F2 equal to F4, F4 equal to F6, and F6 equal to F8. So those are 3 relations, and they must be counted. Okay, if we calculate our degree of freedom, 14 minus 8 minus 2 minus 2 minus 3, and we end up with a degree of freedom of minus 1. Which essentially tells us that there is more than enough information to actually solve this entire process. However, let's look at our overall balance. Okay, that's drawing a balance over the entire system. That of course will neglect stream 3, 5 and 7. So let's count the number of variables. We have 1, 2, 3, 4, 5, 6, 7, 8. So 8 variables. We have a maximum of 2 components associated with this entire process, so our maximum is 2. There are 2 specified compositions and flows, okay, for stream 1 and 9, which crosses our overall box. And also note that in the case of our overall balance, our subsidiary relations are very relevant because they are relating to the streams that will be involved in our overall balance. Okay, so we have our 3 subsidiary relations, so they can be counted. And doing the calculation, 8 minus 2 minus 2 minus 2 minus 3, and that's also minus 1. So we seem to be in a bit of a dilemma here. We have all 4 units which are underspecified. They have a degree of freedom that's greater than 0. Yet the process is telling us that there is more than enough information. And the overall balance seems to be overspecified. Is there anything wrong with the overall balance being overspecified? Intuitively, one would tend to think that perhaps it's not wrong. Perhaps they are just giving us more than enough information. So more than enough information, usually the more information the better, right? So since our overall balance is the only one that's, well, less than 0, it should ideally be 0, but it's less than 0. So let's draw up our overall balance and see what we can find. Okay, so here are our balances. If I can look at the total balance, simply adding all the total flows, what goes in must come out. We only have F1 coming in, and the rest of the streams are going out of the overall balance. So we have F1, which is equal to 50,000 that is equal to F2 plus F4 plus F6 plus F8 plus F9, which is 35,000. Okay, so that's our total balance. And since these are all equal, I can simply say all of these are equal to 4F2, and from there I can easily obtain F2 to be 3750 kgs per hour. Let's look at the water balance. Remember, for our water, we have a total of 50,000 at 50% sugar solution, so it's 50% of water as well. So we have 25,000 kgs per hour of water coming in. And we once again have 4F2 of water coming out of the tops of all of these evaporators. And we have 0.35 times our 35,000 coming out at stream 9. Okay, because we have a 65% sugar solution here, the remainder is 35%. However, from this balance we obtain an F2 of 3187.5 kgs per hour. Ideally, or not ideally, in reality, our F2 should be the same, it should be equal. So we seem to be getting an inconsistent result here. And this is the consequence of having an over-specified overall balance. So let's look at our degree of freedom table once again. And you can take this as a rule that when it comes to your degree of freedom table, your process can be over-specified. Okay, that is quite alright to have your process being over-specified. However, your overall balance can never be over-specified. If it is over-specified, it means that, or it ultimately will mean, or it will result in an inconsistency in your results. Okay, the results will not make sense. Something will be inconsistent. And the same occurs with our units. All of our units must either be 0 or greater than 0. If any one of them are over-specified, it will ultimately result in some inconsistency occurring in the system. Okay, so we can conclude that in this example, this particular process, the information that we are given is not entirely valid. Okay, so bear that in mind when when solving problems. If you are getting negative degree of freedoms for any of your units or for the overall balance, then either you have done something wrong or the problem or the system that you're looking at has some invalid specifications. The process can of course be 0, it can be greater than 0, it can be less than 0. Okay, that will not indicate anything regarding the validity of the specifications in the problem. It will, however, indicate that the process may be solvable or not, depending on whether it's greater than 0. Okay, so to summarize, if something is underspecified in an individual unit, it means that the balances for that particular unit cannot be solved independently of the remaining units. Okay, so if your degree of freedom is greater than 0, the balances for that particular unit can't be solved completely. However, regardless of the degree of freedom of the plant, of the process, the degree of freedom of each individual unit must always be non-negative. If any individual unit is overspecified, the entire problem is incorrectly specified, and we will get inconsistent results.